Okay, let's do some random program. Send this to the chat. So the graph is really small. Is let's see, 3 by 3, right? 3 by 3, and how many states we need if we are going to use dynamic programming? If we are going to put a node here, then this node will change. This. So I care about the 1, 2, 3, first 3 nodes we have, and that is it. We do not care about the nodes before that, right? We don't care this node anymore because following operations will not affect this node state at all. Cool, that's great. So dynamic programming it is, and it will have how many dimensions? The first dimension we're going to have is the RNC of the current node, row and column, right? And we are going to have the state of the last 4. Let's see. Because in total we only have 9 digits, so we can just convert the 9 digits to a binary number, right? And it will be 2 to the power of 9 states, right? And what do we need to calculate? We need to calculate, let's say f is the minimum number of steps we need to convert this state to 0, right? Okay, then in that case we don't need this to RNC, right? Because we can change, we can flip any of the nodes in the 3 by 3 graph. Let me see. So the initial state is, let's say the initial state is 0, 0, 0, and we are traveling from bottom to top. The second state will be change one of them, right, like this, and the second one of the step can change another few, right? And we are going to calculate the minimum step to each of those status. And when we traveled all of those states, the search stops, right? And we can output F the initial state. Okay, I guess that's it. Minimum number. Let's see my notes. Okay, BFS and bitmask. Right, so that's it. Find the longest awesome string. Let's see. Okay. So a awesome string is a string has some characters, and each kind of character has a counter, and the number of even counter can be as many as it is, and the number of odd counters should be less or equal than 1, because if we have two odd counter, that means we kind of have something like this, and this cannot be converted to a palindrome no matter what you swap, right? So that means this condition is the only condition we need to satisfy. We don't care about this condition because the number of even counters can be anything, right? So let's move on. Return the length of the maximum length. Awesome substring of S. Okay, so substring, right? How long is the string? 10 to the power of 5, quite large. So that means we need a O n log n algorithm, right? So awesome substring. What we gonna do? I see. Actually, it might be 1000 multiplied by 10 to the power of 5. I think if we can maintain this magnitude of time complexity, we can still pass, right? Because we only care about a counter, whether a counter is odd or even. So we can have when we scan from left to right of that string, for for each prefix, we only care about the odd and even state of a counter, right? If it is 0, then the counter of 0 is even. If it is 1, then counter of 1 is or counter of 0 is odd. So as this one denotes the even and odd state of number 1 and number 2, number 3, number 4. So we only need to record the 10 digits odd and even states. And for each of the prefix, we're going to have a state like this. And when we have a state like this, we are going to, for each state like this, we are going to record the first appearance of this state. And when we reach any of the states, we are going to find all the states that uh, is valid when paired with the current state, right? Because some of the previous state can pair with the current state, and the result can satisfy the condition we discussed here. So the condition we discussed here is essentially means the number of ones in the state should be less or equal than 1. And if we subtract one of the previous state from the current state, That is the state of the substring, right? So in this way, we're going to find all the substreams that satisfy this condition, right? And for each current state, we are going to find a valid pair at most 1,000 states, right? Because there are only 1,000 states there. Okay, let's see. Time O 10 to the power of n? No, 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 no. Huh. Yeah. So for each of the states, the valid previous state can only the number of valid previous state is not going to be greater than 10 plus 1, right? Let's see, just to make sure. Oh, yeah, that's right. So the 10 possibility here is we are using one of the digit as 1, right? There are 10 possibilities, and the one extra possibility is that all of the digits are 0, right? So we at most has 11 valid previous states. So that's it. When we iterate through all the states, um, when we iterate through all the characters, we're going to find its current state, and there are at most 11 valid states that 1 appears before, and 2, it can pair with the current states, and this way we can find the valid substring, and we are going to record the maximum substring. Cool, I guess that's it. So that is that. Let's move on to the next chunk to make sorted. Did I? Oh, I did this before. So let's see. I might already forgot it. Given an array, we split the array into some number of chunks, individually sort each chunk. After concatenating them, the results equal the sort array. What is the most number of chunks that could be made? we could have made. So splitting 5, 4, 3, 2, 1 into 2 or more chunks will not return the required results. Okay, I see. So it needs us to split the array into some chunks, and we're going to sort each of the chunk, and after concatenating them, the result should still sorted. Okay, how can we split the array? What is the most number of chunks could we have? So let's see. Let's take the second example. So we can put these two in a chunk, right? Why can't we do that? Let's take another example. So in this case, we're going to sort the first three and sort the last two. Why can't we sort the last three? Let's see, because the prefix maximal of the array is okay. So the minimum of the prefix is 2, 2, 1, 1, 1. Hmm. And the minimum of the suffix is 4, 4, 1, 1, 1. Interesting. No, 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 no. This is weird. Let's try another example. If we have 1, 3, 2, 4, 5. That means the prefix minimal is 1, 1, 1, 1, 1. Post minimal suffix is 4, 4, 2, 2, 1. Weird. Very weird. So how are we going to solve this problem? So we can map the array into some continuous continuous array, right? And the array starts from 1, and we need to check the suffix minimal is 4, 4, 4, 2, 2, 1. And we are going to scan from left to right. If it is 1 and equal to the suffix minimal, that means this guy is already the biggest guy. Okay, so we can cut here because this guy is already the minimal guy in the suffix. Let's see. Since it is already the minimal guy, that means we can cut here actually, right? Because no matter what you sorted after this guy still will be the smallest, which is less than all of the numbers come after it, right? So we can cut here. Then we're going to check the next one. The next one is bigger than suffix minimal, so we cannot cut here, but we can cut here and here. So 3 cuts. All right, we found the solution, right? Cool. Let's see. What did I do? Yeah. Oh, I even calculated the prefix minimal. Why did I do that? Oh, I actually calculated the prefix maximal. Why did I do that? So, oh, I see. We need to check if prefix maximal is small or equal to the suffix minimal. Interesting. Yeah, that makes sense. That actually makes sense. Cool. I need to revisit this one. Yeah, so why is that? Because the suffix minimal only makes sure that this guy would be the on the left side of all these guys, but it cannot guarantee that there is not a really big guy at the left of this guy that is bigger than some of the numbers to the right, right? If it is too big, then we have to include it in the sorted in the chunk, right? Cool. That is why we need to keep two arrays. One is minimal suffix and one is maximal prefix. Cool. Nice problem. Interesting. Very interesting. Let's take a look at this one as well, just for fun. Is there anyone watching? Yep. Oh, two people was watching. Okay, so the substring should be in the format like a palindrome. So, I mean, the first one should be equal to the last one, right? Okay. How are we going to split it? Since we are going to split it into k chunks, what is k here? Return the largest possible value of k. Okay, the k is as large as the length, right? So it looks like another dynamic programming problem, and what we are going to do is to find the state first. So let's see. Okay, if we are going to transform, if we are going to chunk I to j, then we should make sure yeah, so this means the maximal chunk. This is the maximal of the number of chunks for S I to J, right? And we are going to return F 0 to N minus 1, right? And we are going to make the first chunk the length of the first chunk is 1, right? And we are going to check the first character and the last. Then try length 2. And we are going to try the prefix of the first two and the suffix of the last two. Okay, we need to check if they're the same. If they're same, then we can recursively solve I plus L and J minus L and the result of this kind of chunking is this guy plus 2. Is that right? Yeah, I think so. Let's take a look at the solution. Longest chunk. Use rolling hash to improve. Interesting. Left to right. Looks like it, right? So prefix, yeah, we can use rolling hash to check if the prefix equal to the suffix, right? Cool, and this is the transformation for transformation formula, right? Cool, I guess that's it. Cool. I guess that's it for today. Let's take a look at the dynamic programming tutorials. I want to get myself familiar with the terminologies. Let's make sure you guys can also hear the talk. Right? Let's see dynamic programming. I need to watch a really simple introduction. Introduction.
Hey
Yeah, only
everyone,
7 minutes.
welcome to the Dynamic Programming Lecture Series. In this tutorial, I am going to cover Introduction to Dynamic Programming. What is dynamic programming in programming world? Components of dynamic programming. Characteristics of dynamic programming, which includes optimal substructure property and overlapping subproblems.
Overlapping subproblems. So what we have in this formula, this guy is the
Dynamic
overlapping
programming methods,
subproblem.
top-down with memoization and bottom-up with tabulation. Before moving ahead, make sure you have subscribed to this channel and click the bell icon to dynamic
Now I
programming.
don't know
Let's
why.
do some quick exercise first. To get the feel of dynamic programming, writes down 1 plus 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 1
What?
equals on a sheet of paper. What's that equal to? Counting 8, writes down another 1 plus on the left.
What
What
the
about that?
fuck are you talking
Dynamic
about?
programming is just a fancy way to say remembering stuff to save time later. This conversation has the essence of dynamic. Remember your past. Let's see what is dynamic problems in polynomial time for which a naive approach would take exponential time. Let's take the very known example Fibonacci numbers to understand a little bit more. 1, 1, 2, 3 occurrence formula. A naive recursive implementation of Fibonacci function has time complexity of 02 raised to the power n imputed value in the table for caching purpose. Statistics of a problem that help us to identify whether d be obtained by using optimal solutions of its subproblems. As
A given problem has an optimal substructure property if an optimal solution of the given problem can be obtained by using optimal solutions of its subproblems. Okay, yeah, that is the key point.
we know to calculate the nth Fibonacci number we use below formula, which clearly shows that a problem of size n has been reduced to subproblems of size n-1 and n-2. It means Fibonacci numbers have optimal substructure property. Overlapping subproblems.
Optimal substructure property. This terminology I had to remember. Optimal substructure property. Yes, that is something we need to remember. I'll record it in my algorithm. Dynamic programming. Cool.
Subproblems are a subset of the original problem. Any problem has overlapping subproblems if finding its solution requires solving the same subproblem again and again. Let's take the same example of the Fibonacci numbers. To find the fib 4, we need to break it down into the following subproblems. Storing or caching, and solve the recursion. The original problem is computed. Let's apply tabulation to our example of Fibonacci bottom-up dynamic programming approach. Share with your friend. Example of fibs first. This is typically done by filling up all entries in an n-dimensional table. Based on the results in the table, the solution to the original problem is computed. Let's apply tabulation to our example of Fibonacci the problems that may be.
Okay, guess that's it. Do they call it a formula in dynamic programming? Deciding the state, yeah. Formulating a relation among the states. Formulating a relation. Yeah, that's the right terminology we're going to use in the interview, right? We need to find formulating a relation among the states. What is the formulation among the states? Okay, I guess that's it. Thank you for watching. That is all I have for today.